Okay, 1, 2, 3, we're back. Can you hear me? Okay. I think I need to share the screen again. Okay. Good. So here we are. Okay. So now we know that in order to calculate value at risk parametric way from explicitly specified distribution, we can use just one line of code, applying PPF method from Stotz, and that's it. Nothing special we need to know uh, except the class of the distribution and the level of confidence that we apply to value at risk. So in order to define corresponding quantile measure. So far uh, we've we could do all the calculations using only one-liners. So dealing with an empirical distribution, we used only one line of code to find value at risk on discrete distribution. We applied just quantile methods. We also applied just one line of code to calculate expected shortfall for empirical distribution. However, things a little different for estimating expected shortfall in parametric way, because let me remind you that expected shortfall technically is a conditional expectation. So in order to calculate expected shortfall on empirical distribution, there is nothing hard math is needed, because everything that we need to do is just to find observations where losses were greater than expected shortfall. I'm sorry, value at risk, and just take empirical average. Just take mean and nothing else. It's very easy. But if we would like to assess expected shortfall dealing with entire distribution, actually we need integration, because we need to calculate expectation in the tail. So actually we need to specify part of the density function. We need to construct integrated function as a combination of value of random variable and its weighted value with density function, and then actually apply the integration. And in this case, we need a little more than usual. We will. It is offered to apply quad integration methods from SciPy. So what we actually need to identify integrated function. As you can see in the formula, we integrating x times density function of x over the tail, left tail. So the limits of integration from minus infinity to value at risk. Okay. And density probability function actually is specified numerically in stats. So if we come up with some probability class. So for example, normal distributions or student distribution, Gumbel distribution, any other class of distribution that can be represented with this method, PDF. So we can define density probability function of fitted distribution this way. Then we multiply it by x. Well, x actually the random variable, which in our case represent losses, profit and loss. So it's our returns. And we also have to reweight the probability density probability function by probability mass concentrated in the tail of the distribution over which we integrate in order to find conditional expectation. Okay, so that's realized in this formula, in this code. So actually, to do some alternation, what you actually need to do, you need to specify fitted distribution. You should do it somewhere here in this cell. In our particular case, we deal with a normal distribution, so the fitted distribution here is normal. So I'm trying to calculate expected shortfall over why there is minus before x. It's just a matter of convention. So Ekaterina asks me why there is a minus before x in formula of expected shortfall for parametrics. Actually, you may pay attention and see that minuses occur all over the way. Why we usually use this minus? Just because we understand that in terms of returns, losses are represented with the negative values, but when we can calculate VAR, or expected shortfall, we are clearly speak of only losses. So we actually talk about the losses. So it's quite obvious that we would like to represent result in terms of positive values. So for example, if someone asks me about value at risk on market portfolio and I say 5%, everyone will understand that I mean 5% of losses. So it's just a matter of convention how to represent measures, risk measures, and convention is that they're supposed to be positive. But once distribution is defined on an axis where negative values represent losses, we just multiply those results by minus one, just to keep values positive for expected shortfall in value at risk, because they already imply for us that they represent magnitude in the quantity of loss. That's it. So for example, if I'm going, so for example, when I deal with the credit risk, actually my distribution represents only losses. So there are no profits on the chart at all. So the entire distribution placed within positive half of the axis. In this case, I won't need to multiply potential values of losses by -1 in order to keep value at risk and expected shortfall positive. So it's just a matter of convention, nothing more. Okay. All right. So now let's apply this formula and see the value. Let me add the value to the legend because I think it's not obvious what the values are. This is my mistake, I guess. And let me get it this way. Okay, this is minus expected shortfall. Oops. Let me round it to. And I also added to the legend in case of parametric estimation. Probably I don't need this anymore. Yeah, I don't need this anymore. I don't need this minus. Okay. So what I can see here, okay. So here's a funny story. Remember when we were talking about value at risk, its empirical and parametric estimates, we actually found out that parametric value of 95% value at risk is greater than empirical estimate. So it's pretty clear can be seen from this figure, right? However, parametric expected shortfall for the same particular case is going to be less than empirical one. So we always have to keep in mind that dealing with the distribution, first of all, dealing with the distribution choice of probability distribution, actually we can manipulate the result. So it's pretty easy to understand that in terms of goodness of fit, like we can apply any statistical measure or Q and Q plot, as we've seen before, and all these indicators may show us that our choice of distribution fits our data pretty well. But the point is that our distribution actually fits well data that we not so care about. So probably you understand that the the greatest extent to which any indicator will illustrate and demonstrate that our model fits data well will be determined by the central part of this distribution. But that's not the part we actually care about. We think about the distribution in a tail, so we care about the results in a tail on the tail, and we actually don't care much about losses occurring in this part, because you clearly can understand from empirical losses, from empirical way of estimating VAR, that only thing that is matter for that matters for the estimation is how many points, how many observation will fall below this value and how many above this value, regardless of their magnitudes at all, right? So for example, if I fix the value that represents empirical estimate of value at risk at this point, and absolutely change the values of extreme losses, So for observations that are worse than my level of var, and absolutely change values of those observations with profits or not so severe losses, actually nothing's going to change according to the value at risk um, estimate. But everything is going to change if I'm going to fit the distribution, because distribution and its form and um, their parameters will be defined by the full set of the observation, right? Because actually I fit my um, distribution uh, on the whole sample. So I'm trying to fit the entire shape, right? Is the number of proportion on the left important? Yeah, absolutely. So for example, if I add any extra observation on the left, so the balance of the observations worse than var, current estimate of var, and observations better than current var will change, and probably that will shift value at risk estimation to the different point. Actually, if you put additional observations on the left, so you actually put another extreme observation, it will actually tell us that now probability mass on the left tail is higher, and probably that means that value at risk should shift to the left, so to the greatest, to the greater values, okay? Otherwise, if I put another good observation, pretty favorable, maybe I add to the sample day uh, when I experience profits, so a happy day, the balance changes again, and now the balance is changed into in direction of favorable outcomes. So the value at risk probably should now shift to the origin, to the negative values with a smaller magnitude. All right, and that's the point. That means that if I have empirical distribution and I, for example, don't want to uh, make my um, estimates very sensitive to the entire shape of uh, empirical distribution, probably I should stick with empirical distribution and empirical estimates. And that's what constitutes historical simulation method of calculating value at risk and expected shortfall. This is the one of the classical ones and mentioned in international regulation like Basel III. So some of the industry accepted methodologies are based on empirical distributions. So they based on historical simulation. Another way, if I would like to incorporate all the knowledge about the of the entire form of empirical distribution, and I think that those observations matter as well, at least um, to the extent that I'd like my estimates to be sensitive to the new data, probably I should fit some distribution, because those estimates will be affected by the all observations in the sample. But we have to keep in mind that fitting distribution will mostly deal with the most populated part of the of the possible returns, and the distribution will be mainly determined, and parameters of this distribution will be mainly determined by the typical observations, so the most probable ones. But we are more concerned about behavior of those distributions on the tails, and that will make us to tend to pick distributions with the heavier tails, because, for example, as you can see in this particular example, using normal distribution actually allows me to be more conservative in terms of value at risk, at least on 95% of confidence. Maybe if I change this confidence level, I won't be able to get more conservative estimates compared to the empirical one. But we'll see. But at the same time, if we talk about the expected shortfall, I can clearly see that parametric estimate from normal distribution comes to the underestimation of the risk, because empirical estimate is much higher than theoretical one implied by the normal distribution. All right. So now let's do a little experiment. Let me change the type of the distribution. As you can see, we used normal distribution all the way, and now let me use another one. Let me use t-distribution. Everything that I need to do is just to specify another distribution here. I can agree with you if you say not very effectively organized code, because I can actually specify the distribution type just in one variable. Well, I can agree with you, but let's change this course a little bit later. All right, and let's see what's going to happen. Okay, now I apply new distribution. Okay. All right, now we can see that parametric distribution, parametric estimation of value at risk, pretty close to the empirical one. And this particularly tells us that at least on 95% of a confidence, t-distribution fits our data pretty well. And that's what we observed using other graphical diagnostic tools for diagnostic of our model. Okay, and now let's do the same for expected shortfall and see what's going to happen. Oops. Yeah. Okay, and now you can see that picking another distribution, namely the t-student distribution, actually let us obtain more conservative expected shortfall estimates, even compared to the empirical one. And probably you remember that dealing with a normal distribution, we actually had some less conservative values. Okay, that means that actually picking distribution matters a lot, but at the same time, we have to understand that we cannot be fully ensured that distribution that we pick is actually suits our purpose well, because we actually, everything that we can do so far is that we can compare the values of different estimates, and we have nothing to do with actual performance of the risk measures. So we never performed the any validation techniques on independent data. So that's the topic of the next lecture that I'm going to switch to. Also, I have a brief description here for the case of Monte Carlo simulation. I'm going to leave it for a seminar because actually it actually describes the case when model cannot be treated as an analytical one, so I cannot integrate the density probability function. I cannot easily define inverse function and find quantile, but at the same time, I can use this model to generate a sample as big as I need to approximate actual theoretical distribution with any degree of precision. And after that, apply just well-known to me empirical ways to estimate VAR and expected shortfall on discrete distribution, which is pretty big and close to the continuous. Okay, so that's just a couple of lines of code. First line represents generating the sample containing 10,000 scenarios, 10,000 points, and then we actually can perform getting empirical quantile on this distribution using standard quantile function. And as you can see, value at risk for 95% of confidence for this size of sample is pretty close what we're gonna get from parametric estimation. Okay, so this is kind of the same. We can easily see this from here. Okay. All right, so now let's move to the next topic. I'm going to change the notebook, switch to another notebook, and you can also follow another link. I'm going to provide it in chat. Okay, here's another link. Okay, please follow the link and copy the notebook to your Google account so you can modify the content. All right. So the next topic is the validation of risk measures. What we actually mean by validation. What we've been doing so far is applying model. We try to extract some information on risk measures that can be useful for economic decisions, but everything that we could do is just perform the calculations, see the result, and compare results from different models among themselves. And at the same time, we had nothing to say about the quality of risk measures itself. Yeah, absolutely true. We can uh, conclude on goodness of fit of particular probability distribution that we chose to represent our data, but that's it. There is nothing to do with risk measures that have their own properties and can be assessed from point of view of those properties. So we actually very concerned how those properties that we anticipate of all our risk measures, all our risk estimates, uh, to reveal themselves in applying in a fully independent manner. So, so the idea is not to deal with a single observation, because what we actually can do, we can, for example, estimate value at risk of potential losses for tomorrow. And after that, we can look at the tomorrow's result and see the relationship between my risk measure, the value at risk, which is kind of measure extreme losses, at least the barrier between critical losses and the typical losses that I can expect with a specified confidence level. So I have an observation. I have actually realized return, and I have value at risk. So the quantile measure of those returns that I could estimate before actually taking this risk on and see the realization of the risk. One of this just single observation won't tell me anything. Okay, for example, I have value at risk estimation, and then I observe profit. What it says to me? Well, nothing particular. Probably I'm a very lucky guy, and uh, I've been uh, I've been blessed to get profit today, but probably I will be damned tomorrow and suffer severe loss. What if I observe critical losses today? Nothing again, because maybe I'm unlucky. Maybe tomorrow I see the better day. So the idea of validation process is to see in a series of experiments of applying risk measures and observing corresponding to them realized losses, and infer on quality of the model that produce those estimates from the series of experiments and the relationship that this series actually demonstrate between risk measures and realized losses. Um, Let me tell you that expected shortfall is a very complicated risk measure in terms of validation. So we go into Liberty side for this course. Probably this is a topic for a master's degree, but we go into discuss in detail the validation process for value at risk. And that's what we're going to do right now. I'm going to use the same example as a base for an explanation and illustration. So we're going to work with uh, investment in a single stock, namely Apple Corporation, and we go into use data over 5-year history, containing all daily observations on the prices. Okay, so what I'm gonna do, I'm going to fix one way that I'm going to calculate value at risk on a daily basis. it means that I'm going to construct value at risk estimation for the next day, then observe realized losses and reevaluate and do the calculation again for the next day. So this is a kind of rolling window that allows me to calculate risk measures and then perform their comparison to the realized losses on a daily basis. Okay, so the way I'm going to calculate value at risk is implemented in this single line. Everything that you need to understand so far that this is the empirical calculation of value at risk in a rolling window with a length 1 year or 252 trading days. Okay. So what I'm technically doing, I'm considering previous 252 observations just right before moment today when I construct my portfolio. I estimate future potential losses with empirical distributions based on those 252 days. Then I calculate value at risk and assign it to the next day over which I'm going to hold my portfolio. And then I observe the result of holding this portfolio over 1 day period and register 1 day realized losses on loss or profit on portfolio. And then I'm going to add this realized losses to my history. And then I'm going to apply again this formula again. So I'm going to switch the window. I'm going to take another 1 year of previous observations, including my new observation on realized losses and dropping one very old one. Okay. And then I'm going to do this all the way the historical data I have. Okay, so it's going to give me this picture. So this blue fence is. Could you please repeat the algorithm briefly? Bullet points, sort of. Okay. Andrei, I can explain it to you again with this chart, I guess. So what do we have here? We have realized returns. This is my historical data. And I also calculate value at risk for those observations, for those days in a retrospective way. So what I'm doing here, so for example, let's take a look at this date where I can see realized losses and some VAR. What I'm doing, I'm taking historical data of 1 year. So I take previous 252 observations. So this part, I construct empirical distribution based on those returns. Based on those on this empirical distribution, I assess 1 day value at risk empirical way. So I use empirical estimate of value at risk and use it as a risk measure for the next day. Okay. When then I observe the realized return on that day, added to my sample on a previous step, and calculate empirical value at risk again for the day after tomorrow. So that means I'm going to run rolling window with the length of 252 observations. It's going to run along the way my historical data. And for each date, starting from here, I'm calculating value at risk as empirical quantile of previous 252 days and use this quantity as the risk measure for the day, okay? So I can actually observe a lot of points where I have risk estimate, so the VAR estimate, and I also observed realized losses. So I kind of simulate the real life going and real life application of the model. So I put myself in somewhere in a point in past. I imagine what would happen if I had only the information up to this date. I use this information for calculation of risk for the upcoming day. Then I imagine what return I'm going to face if I live this day. So I add this information to my sample, and then I can rerun this algorithm all the way going from previous dates to the current date. All right. That's why I can actually observe all the realized risks represented by realized returns, and I have risk measures for those dates. Okay? So I kind of constructed series of experiments when I have value at risk measure and observed actually realized returns. All right? So this is a kind of idea. So every day I kind of simulate the actual course of the life. So what would happen if I construct my portfolio at some point in the past? So for example, constructing my portfolio on let's say on 9th of January, for example, I could estimate for the next day, I estimated my potential losses like 3%. And then I actually realized that I've never observed that kind of losses. Actually, I observed profit. Another day, probably I observed some losses, but they are not so great as a VAR estimate. Other days, probably I'm going to see events when actual losses actually hit my value at risk estimates. So I experience extreme losses respectively to typical losses bounded by value at risk. Okay, and that actually provides me with a very useful information. This series tells me how often or how many times in a series of experiments, on a series of days actually applying value at risk model, I can observe very tough days, extremely severe days when I experience losses not covered by value at risk. All right, and this information actually helps me to make a conclusion on quality of those risk measures that produced by this model. Because what I know from the model, I actually know that the value at risk itself, it's not the limit of the losses. It's just some boundary of typical losses that's specified by my confidence level. And regarding confidence level, I choose. So for example, I use 99%, confidence interval. That means that probability of observing day when actual losses are higher and severe than and more severe um, than expected by value at risk is 1%. So actually there is a probability to observe critical days, and it's okay to observe them. But the question that we can actually, but the question that we can formulate is how many days with the severe losses is okay to observe in order to say, okay, this number of hits and this number of critical days are in line and consistent with my expectation of probability of observing this day is, for example, 1%. And this actually led us to construct a formal statistical hypothesis testing procedure that allow us to statistically assess if the losses that those days then when losses greater than value at risk, they occur not very often to say that my expectation of for properties to be ensuring 99% of confidence it is inconsistent. Okay, so let's take a look at this graph again. But now we're going to mark some days when we actually observe hitting the line of value at risk by observed losses. So this is the extreme days. Yeah, we know that they can occur, and that's okay. But now let's put a formal framework to answer the question: is if the number of those days are in line and consistent with the probability of value at risk being hit. So let's first of all calculate the entire number of observations. So the length of the historical period over which I calculated value at risk and observed realized losses. So this is a very easy to do. Now we understand that there are 106 observations. So this is the length of this series. And let's calculate how many events of hitting VAR we actually observe. And the answer is 17. Let me remind you that confidence level of the value at risk here is 99%. That means that anticipated probability of observing hitting this line is 1%. So let's see how what's the frequency, what's the observed empirical frequency of value at risk hits in our sample. And it's very easy to see that it's what does 106 mean? Here's a question from Mikhail. What does 106 means? Mikhail, this is the number of observations when I have value at risk estimate and I have observed return of this day. Okay, so let me remind you what I'm trying to do. I'm trying to collect as much data as I can of pairs of observation, prior estimate of value at risk for the next day, and actual realized losses from holding portfolio over 1 day. So I have 106 days when I had the distribution, when I have a value at risk estimate, and when I observe actual loss. Okay, so this is the line. This is the length of the sample where I can observe this line, which is var line, and all these realized losses. Okay. So actually, you can think about it as the 4 years of historical data where I simulated my behavior of producing estimate of value at risk for the next date, for the closest date, and then observing actual loss. All right. So, for example, I expected with 99% of probability to see losses not greater than 5% for tomorrow. And after that, I observed 0.5% loss on that day. Okay. And I have another 1005 observations like this. So this is the sequence of the date when I assess risk and then fix and register the realization of risk. Okay. So let's see how many hits do I observe relatively to the size of sample. And actually, I understand that I observe 1.7% of days when realized losses exceeded value at risk estimates. And here's the question. I remember that probability of observing such dates is 1%. And I empirically observe 1.5% of such days. So what does it tell me? Is it available and save app have 18 hit statistical randomness? No, I don't think so. I think probably you altered this code somehow. No, I don't think that that should happen. Mikhail, there is no randomness about result. Kind of interesting. Really? Let me run the code myself and see what's going to happen. Maybe I changed something here and forgot to recall all the functions. Let me see. Take. Yeah, probably I changed something and I forgot to just rerun. But I forgot what I changed here. And what I changed here. Not sure. Yeah, at least now we're on the same page. So we have, yeah, we have 105 observations and we have 18 hits. Well, it doesn't change picture drastically, at least all the results and all the conclusions that we have to make out of this example. They're still the same. All right, so here is the question. Okay, I observe 18 hits out of 105 days. So is this number big enough to say that my value at risk is exceeded too often to think that actual probability of hitting VAR is 1%? As a matter of fact, we can perform formal test, and this procedure is called backtesting, and it has binomial test in its core. And this test actually is pre-realized in stats module. So you can call binomial test and run it into specifications. One of them with two-sided alternative hypothesis, and another one with a one-sided. So what is the null hypothesis of this test? Actually, the null hypothesis is that the probability of hitting VAR is actually consistent with our anticipations and our expectation of the probability VAR being hit is 1%. So if we choose 99% of confidence, the probability of observed losses greater than VAR is 1%. And that's what we state in the null hypothesis. From this hypothesis, actually, we can infer that the number of hits that we observe over our sample has binomial distribution with a probability of success 1%, right? Which corresponds to 1% of extreme losses. So, for example, if I have 105 observations, or I can call them 1005 Bernoulli experiments, like tossing a coin, where the probability of getting tail is 1%, for example, and it represents the probability of VAR get hit. So the number of hits that I observe over the sample of this size is a binomial distribution with 1005 number of experiments and probability of success 1%. And this null hypothesis states that this null hypothesis actually conceptualizes the idea that my model produces correct numbers of for VAR. So it produces correct and precise estimates of value at risk. Okay. So all the randomness is driven by the nature of Bernoulli experiments with a probability of success 1% in a series of experiments containing 1,000 fine experiments. That's it. And this is the null hypothesis. And this hypothesis produces me the core distribution, which is binomial. That's why we talk about binomial tests. And from this distribution, I can actually specify critical zone in order to be able to test alternative hypothesis. And alternative hypothesis I can formulate in the two following ways. I can formulate two-sided hypothesis and say that, okay, alternative hypothesis is going to be that actual probability of hitting value at risk estimates produced by my model, this probability is actually any different from 1%. So it's either significantly greater or significantly lower than 1. All right, so it's just inconsistent with my perception of having estimates that should be hit with a 1% of probability. Another way of formulating alternative hypothesis is to say that actual probability of hitting VAR is greater than 1%. So I don't care in this case about actual probability of hitting VAR being too low, because in this case, it actually means that my VAR estimation is too conservative, and it's hit not that frequently to think that my confidence level is 99%. Probably it's a higher confidence level than 99% because the probability of hitting VAR is less than 1%. But what I actually care about if I estimate value at risk is I'm afraid that actual probability of hitting VAR is greater than 1%. And because this case means that my model underestimates actual risks, and confidence level that this model gives me actually less than target one. So if I'm expecting to have 99% and of confidence, and I see too many hits over my sample, that's gonna make it's gonna tell me that my model actually provides me with a lower confidence level, and probably I should do something about this model. All these two hypotheses actually make sense, and they can be used during the assessing quality of the risk model, but in two different ways, and the result is going to provide different answers. And probably we'll care about these two alternative hypotheses in different contexts. So for example, if I am developer of the model, and for example, I've been given a task to develop model ensuring confidence level of certain degree, so for example, 99%, and I actually concerned about to provide my client with a model that consists with this confidence level as as close as possible. That's why probably I would like to ask two-sided for two-sided alternative hypothesis. Another picture arises from the regulatory purposes because regulation usually sets critical value for some parameters. So, for example, central bank may ask banks under its supervision to provide internal models that ensures confidence level not less than particular one. In this case, banks probably interested in one-sided alternative hypothesis. Okay, and so applying this binomial test, we actually come up with some p-value, and I'm sure that you are familiar with providing hypothesis testing, and you know how to conclude on quality of the result based on the p-value, right? So here I can provide you with a little hint how to deal with this. So we usually test our hypothesis on particular level, and in this particular case we state 95% of confidence, right? So leaving 5% for error first type. So when we can reject correct hypothesis. So, and we can compare this p-value with the critical value, and actually in the process of validating risk models, we have several levels. So the 5% here is just a regular level that we use to apply when we run our hypothesis and testing hypothesis in a statistical way. So this is the way we actually use, this is the level we use to accept the hypothesis. So for example, if we observe p-value greater than this value, we usually accept null hypothesis and say that our data provide us with evidence that null hypothesis is correct, at least statistically, right? And that's what we call green zone regarding the validation process. And if the null hypothesis is correct, we usually say, okay, we're going to keep this model at least as the one of those we feel comfortable with. So this is the working model. It provides us with target confidence level. What's going to happen if the p-value is less than 5%? And here we have two areas. One of these areas are bounded by pretty small but still realistic amount. So it's kind of 1 basis point. So it's 1/100th of a percent. So if we observe pretty small p-value but still reasonable, we usually question our model. We still think that rejecting null hypothesis might be because of the bad luck. So actually we're observing error of the first type. In this case, we usually put our model on quarantine, and we're trying to provide additional adjustment just to make it more conservative, but we still can use it in a practice. But if p-value is less than this value, this critical value, second one, this is the red zone. This is p-value that says this is too bad to be tolerated, because the probability of getting that much hits is too low if we believe in the correctness of null hypothesis, that observing this much, this many hits, this situation cannot be consistent with the null hypothesis at all. So that means that model that I'm currently using and trying to test absolutely useless. It doesn't it does not provide any kind of consistency with null hypothesis and anticipated confidence level of the var, and we should reject model immediately. Okay, so we just throw it away and never take it for a long time back into production. Okay. Okay, this is how backtesting works, and that's how we can conclude on the quality of the model producing value at risk. So if the test produces p-value with the pretty high values, at least higher than specified probability of type 1 error, we accept the model and accept the correctness of null hypothesis. If the p-value is small, but not too small to think of number of hits to be that great that is absolutely impossible to observe them in the presence of null hypothesis, then we put the model on the quarantine and provide some adjustments, but still can use it in the production. But if we in a red zone where the p-value is almost nothing and tell us that it's almost impossible to observe that kind of that amount of hits regarding the correctness of null hypothesis corresponding to the anticipated probability of hit and confidence level of the var, we should reject our model completely. Okay, one remark should be done here, a brief one, and then we're gonna go for a break. This test actually is performed in assumption that all the observations of hitting var and performing of the model are independent. That means that this picture actually should be more like absolute random and evenly spreaded cases of var being hit, rather than these sequences of the hits. So that means that if the hit of the var absolute, some of us have similar, going to be here, is it going to be here as well? No, I mean, the validation is not the part of our seminar today. Today we go into do some calculations on expected shortfall and value at risk. This is my answer to Andre. Okay, so that means that before running formal backtest, we actually need to test independence of occurrence of these hits over our sample. Unfortunately, it's not very easy to do because that kind of tests of independence of hits requires very large samples and very vast amount of observations. Usually, we don't have that many observations in our disposal, at least because our future lost actuality and urgency for our purposes. And usually we cannot come up with a conclusive test on independence. But still, I provide a little example, and you can follow this example at home. And we're going to discuss it during the seminar next week. Okay? So I think now this is it for today. Today's lectures are over. I think we're gonna have 30 minutes break now. I'm going to close this meeting and provide you an LMS with a separate link to the seminars, okay? So thank you very much for your attention. I see some of you in a half an hour. Okay? Okay, bye.